All right, so here's a video of your test review for Unit 3. Unit 3, test on Friday and Monday. All right, so here we go. So the arrangement of electrons in an atom is called the electron configuration. Electrons fill up the lowest energy levels first. The lowest energy state of an electron is called the ground state. And this is going to be your off-ball principle. According to the Pauli exclusion principle, two electrons can share an orbital but must have opposite spins, which is why we draw an up arrow and why we draw a down arrow. An atom's blank is a measure of how much it wants additional electrons, so this is going to be electronegativity. The blank energy is the amount of attraction for its own electrons. This is going to be ionization. All right, and both of those trends go this way and that way. Okay. The blank uncertainty, so this is the Heisenberg uncertainty, states you can't know the position and moment of an electron at any one time. All right. So next one, write the electron configuration for iron. So iron is here. Let me do this. Iron is found here, and so we should end at 4s2, and then 3d 1, 2, 3, 4, 5, 6. So 4s 2, 3d6. So let's do iron 1s2, 2s2, 2p6, and then we have 3s2 over here, and we should have 3p6, and then we're getting down to iron's level, 4s2, then 3d6. Okay, oxygen up here, 1s2, 2s2, 1s2, 2s2, 2p4. And then calcium, which is here, so we're getting down to the 4s2 is where we should end this. 1s2, 2s2, 2p6, then 3s2, then 3p6, and then 4s2. All right, and so remember, you have to do all of these notation things without your colored blocked off periodic table, just with the green ones that I provide. So noble gas notation for nitrogen. Nitrogen's found here. Remember, helium falls behind it, and so I'm going to put helium in my notation. My brackets. So then I can start with helium, and I go 2s2, and then 2p3. Sulfur, which is found here, so I go with the noble gas behind it, which is going to be neon. Neon is here, and then I go 3s2, 3s2, and then 3p4. And then potassium is here, so this will be a real quick one because now I use argon, and then 4s1. The orbital notation for lithium. Lithium is found here, so the normal notation is 1s2, 2s1. All right, that's lithium here, 1s2, and then 2s1. So my orbital notation is going to be 1s, and because there's two electrons, one up, one down, and then 2s1, so I put 2s, line, 1 up there. All right. And then sodium, which is found here. Sodium is found here. Normally it's 1s2, 2s2, 2p6, and then 3s1 is its electron configuration. So now I need to open up all those and put my electrons in them, or my arrows in them. So 1s2, 2s2, and then 2p6, 2p, 1, 2, 3 orbitals, up, 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 down, down, down. That gets me through 2p6, and then I get 3s1. That arrow going up. All right. So what is the noble gas for nickel? So nickel is here. We should have argon as my. So these two are out. Argon, and then 3d4, 3d8. We forgot everything up until then. So that one should be it. Yttrium is found here. So noble gas notation for yttrium should start with krypton, not xenon, and then it should be 5s2, 3d1. What orbital is the last valence electron of vanadium? Vanadium is found here, right? And so what is the orbital? Should be 3d3, right? Because we go from 4s, and then this row right here starts your 3d. Okay. What is the correct electron configuration for chlorine? Chlorine should end at 3p6, 3p, well, all of these 3p1, 3p5. I'm sorry, should end at 3p5. It's chlorine. None of these are correct. So that one, we didn't even need to look at the first couple because we knew the endings, right? What do orbitals represent? If it is where the blank are likely to be found, the electrons are likely to be found 95% of the time. All right, next page. The current model of the atom is known as the quantum mechanical model. The Bohr model has been replaced by its new model with further explanation of the sublevels and orbitals. The configuration of this belongs to the element, so 3p1. 3p1 is aluminum, found in group 13 in period 3. Configuration of this, so 2p2. 2p's over here, 2p2 is carbon, found in group 14 in period 2. All right, election configuration notation for blank is this. So if we look at 3p5, here's 3p, 1, 2, 3, 4, 5. This should be chlorine, and there we go. The electron configuration for this one is, if we look at just 2s1, 2s1 is lithium. There we go. Which of the following breaks Alph-Loss principle? So Alph-Loss principle is that you need to fill, you need to fill lower levels before the higher levels. So 1s2 is good for all of them. 2s2 is good for all of them. 2p6, 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 and notice how this is 2p2, and then we went on to fill in these other ones. Well, that breaks his rule of filling the lower ones before getting to the higher ones, so C is your answer. Okay. Same thing here. Which one breaks? So 1s2 for all of them, 2s2 for all of them, counts. 2p6, 2p6 for all of them. 3s2 is in all of them, that's right. And then 3p6, 3p6. This one stops, but all of this was good, so we're okay there. 3p6 is good there. 4s2, 4s2, 4s2. And then this is where we go into, it should be our D level. 3d10, 3d10 is our next level. This one jumps straight into 4p5, so that's not correct, right? So what element is demonstrated here? So once again, when we do these, what element ends at 3p1? Well, 3p1 is here, 3p1 is aluminum. Electrons fill the lowest energy levels first. Electrons within a pair must have opposite spins. The orbital notation correctly represents the valence electrons of group. So valence electrons are these two added together. So there's 3 valence electrons, which is in group 13. Okay. What group on the periodic table does this valence electron represent? So again, you have 2, 4, 6, 7 total here, which is going to be group 17. What group on the periodic table does this represent? And this is the same question as 19, because 1, 2, 3, 13. So put these in order from smallest to largest atomic, smallest, in order from smallest atomic to largest. So atomic radii go this way. So as we go down and to the right to left, we get larger. So in this case, when I find, go down a little bit, potassium, lithium, cesium and sodium, I know that cesium is going to be the largest, so we go from smallest to largest. Cesium goes there. Lithium is at the very top, and then I have sodium, and then I have potassium, because that's what the trend says. Okay? Which of these has the largest atomic radius? So largest atomic radius, boron is here, aluminum is here, boron, aluminum, indium is here, and gallium is here. So indium falls the lowest, so indium should be your answer. Which of the following elements has the highest ionization energy? So ionization energy goes from left to right, top to bottom, including your noble gases. So sodium is going to be all the way over here, so that's probably not going to be it. Chlorine is going to be over here. That could be silicone and magnesium. Chlorine is going to be the one because it falls the highest and most to the right. Smallest electronegativity to largest electronegativity. So your smallest is always going to be your noble gases, but we don't have a noble gas here. And so your smallest, if you have manganese here, potassium here, zinc is going to be here, and bromine is going to be here, so it's going to be in that order. So K, Mn, Zn, and then Br. All right, there we go for that page. And then on this page, which of these elements has the highest electronegativity? So once again, we're looking at electronegativity. Once again, goes this way and up. There we go, this way and up. And then excluding your noble gases. So oxygen is really the only one more electronegative than oxygen is fluorine. So oxygen is your answer. The blank is the distance between the nucleus and the valence electrons. This is your atomic radius. Okay. Examine the diagram. The first thing that is wrong with the diagram is, so what do I see wrong? 1s2, 2s2, 2p6, 3s2, 3p's. The first thing wrong is that we didn't follow Hund's rule here. We should have, not this arrow, we should have 1 in the first one and then 1 in the next one. Okay? The second thing that's wrong is Aufbau's principle, because this arrow needs to fill down here before we go to the next energy level. All right. 29, fill in the valence electrons for nitrogen. Nitrogen is here, so there's 5. So 1, 2, we need to fill that level. 3, 4, 5. All right. Next one, fill in for neon. Neon is, that's full, and then these are all going to be full as well because it's 2p6. Okay. 32, an atom of fluorine more strongly attracts electrons in a bond compared to an atom of calcium. This is because fluorine has a higher, and so these two are going to be out, but these two are where we need to look. An atom of fluorine more strongly attracts electrons. That's the definition for electronegativity. That's why electronegativity is going to be your answer. All right. Compared to the atomic radius of krypton, the atomic radius of neon, so krypton to neon, all right, remember as we go down we get bigger in the radius. The atomic radius of neon is smaller. This is primarily a result of neon atom having, and because we're going this way, it's going to be fewer energy levels. That should be D. Right? Compared to the atomic radius of potassium, here, the atomic radius of calcium, which is here, so calcium is going to be smaller. The atomic radius of calcium is smaller, so that's gone and that's gone. This is primarily because of a number of protons. Because they fall in the same energy level, we can't look at energy levels because they have the same amount. Now we need to look at protons. Explain what an atomic orbital is using the term 95%, shape, electron, and probability. So once again, an atom is surrounded by its electrons. Those electrons are found in orbitals. Okay, those orbitals create shapes depending on their sublevels around the nucleus, where electrons are found 95% of the time. All right, and we can, the probability of finding them is 95%, if you want to add that word probability in there. Okay, the back side of your review, the last page, looking at the EMS spectrum, is which of these types of electromagnetic radiation has the longest wavelength and carries the least amount of energy. So the longest wavelength is going to be down this end. So ultraviolet, infrared is shorter, X-ray, and gamma ray. So it's going to be infrared of these four, because infrared's found right here. Of those four, it's going to be the shortest. Which has a higher energy visible light or microwaves. Higher energy is about frequency, so as we go this way we get more frequent. So light waves are found here, light, visible light, and microwaves are over here, so the more energetic is your visible light. What is the relationship between frequency and energy? Well, this is going to be direct because they both go up or they both go down. If the frequency increases, what happens to its wavelength? So frequency and wavelength have an inverse, so these are opposite. Frequency increases, that means wavelength will decrease. If energy decreases, what happens to frequency? Once again, energy and frequency have direct, so it's one, whatever happens to one, the other one will do the same. So energy decreases, frequency will decrease. What is the relationship between frequency and wavelength? This is going to be indirect, or you could say inverse. Okay. So here at the bottom is our math. So some things with the math. I'm going to write over here to keep separate and do all my math over here. So number one, we have our formula, which is the speed of light is c equals your wavelength times frequency, and then you have your energy equation, which is E equals h times velocity, or sorry, not velocity, but frequency. Now what you need to know is that c will always equal 3 times 10 to the 8th meters per second, and h is Planck's constant, which is going to be 6.626 times 10 to the negative 34th. Okay, that's a 4, not a 9, right? And then this symbol here equals wavelength, and that's going to be measured in meters. And then E is going to be energy, and that's going to be measured in joules. And then you have V, which is frequency, and that's going to be measured in hertz. Now, you might see S minus 1, and that's just a different way of writing hertz. So anytime you see S minus 1, just cross it out and put HZ. Okay, so I'm going to use this as a reference over here. So here we go. Calculate the wavelength and the energy of light that has a frequency of that hertz. All right, so I need to use actually both of these equations. So the first one, wavelength, so I'm going to use this one because that's where wavelength is found. So I know that C is 3 times 10 to the 8th equals, and then wavelength, because I'm going to be solving for that, and then my frequency is 1.5 times 10 to the 15th. Okay, well, how do I get wavelength by itself? Well, I just divide both sides by this to get it by itself. That cancels that out, and then I got to do it to this side as well. So when I go to my calculator, make sure you use parentheses here. 3 times 10 to the 8th, close your parentheses, divided by, both in parentheses, 1.5 times 10, caret button, 10 to the 15th, and I get that as my answer. Now, because I have two sig figs here, right, I got to put this in sig figs as well. So this should be 2.0 times 10 to the negative 7th. And then because it's a wavelength, this should come out in meters. So there's my first answer. Okay. My second one is energy, which I need to use this one. So I know that I need to find E, which means H, which is Planck's constant, 6.626 times 10 to the negative 34th times my given 1.5 times 10 to the 15th. I can put this right into my calculator right away because that multiplied by that will give me the E. So 6.626 times 10 to the negative 34 times 1.15, oh sorry, 1.5 times 10 to the 15th. Enter. And so I get this populated, but I need to have two sig figs, so it should be 2.94 equals 2.94 times 10 to the negative 19th, right? And because we're looking for energy, this should be in joules. Okay. My next question, a photon has a frequency of that, calculate the energy. So this is where we have to use just this one because I know the frequency, now I have to find the energy. Okay, so this is just hertz, that's a good thing, which means I don't need to convert out of. This is just hertz, so that means I don't need to convert out of it, which was a good thing. So I need to use energy, so I'm going to be using this right here. So energy equals Planck's constant, which is 6.626 times 10 to the negative 34th, multiplied by the frequency, which is 2.68 times 10 to the 6th. All right, so I'm going to put that in my calculator. 6.626 times 10 to the negative 34 times 2.68 times 10 to the 6th equals, and here's what's in my calculator. I need to have 3 sig figs because there are 3 right here. 1.775, that 5 around that to an 8 times 10 to the negative 27. There we go. And on the bottom, this is where it gets a little bit tricky because calculate the frequency and the energy of blue light that has a wavelength of this right here. Okay, so because that's nanometers, that's a problem. And also I need to first get frequency to plug my frequency into my energy equation. So that's what I'm going to be doing that one first, all right? So first I need to get this into meters. Well, 400 nanometers equals, and I'm not sure if it's on here, but a nanometer is equal to 1 times 10 to the negative 9th nanometers is equal to 1 meter. So what does that mean? That I need to put this term on the bottom, 1 times 10 to the negative 9th nanometers, because that gets out of that, and then I can put that into my meter. All right, so this answer is going to put it in meters so that I can use this equation over here. So I'm going to take 400 divided by 1 times 10 to the negative 9th. I get that as my answer. Okay, which is 4 times 10 to the 11th. All right, so now I can use this wavelength, this is meters, this wavelength to plug into my equations up here. So the speed of light is 3 times 10 to the 8th, and that equals my wavelength of 4 times 10 to the 11th, and then I should be able to solve for my velocity by dividing both sides by my wavelength. 11th, 11, that cancels out. And when I do that, I should get 3 times 10 to the 8 divided by 4 times 10 to the 11th. I should get 7.5 times 10 to the negative 4th. And this is going to be frequency, so it's going to be in hertz. And then I can plug this into my energy equation to find energy. So I know that energy equals 6.626 times 10 34th. My frequency will go there, 7.5 times 10 to the negative 4th. So I can just leave that in my calculator and then multiply it by 6.626 times 10 to the negative 34th. And so there's my answer right there. And because I'm using sig figs and I start with 1, and actually this should be rounded to 1, so that should be 8. And because I'm starting with 1 there, that's going to round up to 5. times 10 to the negative 37, and then this will be joules because we're finding energy. Okay, so I hope that is helpful.